Hello everyone, welcome to the channel, Mathority here. Today we'll be delving into the notorious gamma function and where it actually comes from. Why does it have the definition that it has? What does this funky integral have to do with the factorial function? Where does the x to the n-1 e to the negative x come from? And why is its integral evaluated at these bounds, and many more questions. If you clicked on this video, you probably have some familiarity with the gamma function. However, I've come to notice that most people don't know where exactly this function originates from, and just take it for granted as if it appeared from thin air. And even if you have no familiarity or knowledge of the gamma function, fear not, for we will be deriving it completely from scratch. So without further ado, let's get right into it. Before we begin our quest to discover the gamma function, let's quickly go over a concept known as integration by parts. And it's simply as follows. The integral of u dv is equal to u times v minus the integral of v du. With this in mind, let's evaluate the logarithm function. More specifically, let's evaluate the integral of the logarithm function, log x dx. Using integration by parts, we can set u equal to log x. Therefore, du would be equal to 1 over x dx. And the dx in our integral would be equal to dv. Therefore, v would be equal to x. And our original integral would just be equal to u times v, which is x times log x in this case, minus the integral of v du. And in this case, v is x and du is 1 over x dx. Therefore, the 1 over x and x cancel, and we just have the integral of dx. And this simplifies nicely down to x times log x minus x. And I'm going to do something interesting, and I'm going to write the coefficient of 1 in front of the x. And technically this also has a plus c term, but for the sake of this video, I'm going to ignore that, and you will see why shortly. Now that we have this, let's move on to evaluating the integral of log squared of x dx. Again, using integration by parts, we can set u equal to log squared of x. Therefore, du is equal to 2 log x times 1 over x. And I just obtained this using the chain rule. And dv would be equal to the dx in our integral, and therefore v would just be equal to x. And our integral would be equal to u times v, which is x times log squared of x, minus the integral of v du. And in this case, v du would just be 2 log x, because the x and the 1 over x cancel out. We can bring the 2 outside the integral, and we just have log x dx. And I forgot to write dx over here. I apologize. And what we notice here is we already solved the integral of log x right above. And so we can plug in our result from the previous integral into this one. And so what we get here is x log squared of x minus 2 times the result from above, which is x log x minus 1 times x. Fantastic. Let's go ahead and distribute out the 2, and we get x log squared of x minus 2x log x plus 2 times 1 times x. Now, let's move on to evaluate the integral of log cubed of x dx. Well, again, using integration by parts, we have u equal to log cubed of x. Therefore, du is equal to 3 log squared of x times 1 over x. And I obtained this using the chain rule. And therefore, we also have dv equal to dx, and so v is equal to x. And applying integration by parts, we have u times v, which is x times log cubed of x minus the integral of v du. The x and the 1 over x cancel out, and we're left with 3 log squared of x. And we can bring the 3 outside of the integral, and we have log squared of x dx. And again, we notice that we've already solved the integral of log squared of x above. And so, as before, we can plug in our result from above. And so we have x times log cubed of x minus 3 times x log squared of x minus 2x log x plus 2 times 1 times x. Let's distribute the negative 3, and we get x log cubed of x minus 3x log squared of x plus 6x log x minus 3 times 2 times 1 times x. I think you're starting to get the idea, but in case you haven't, let's just do one more. Let's evaluate the integral of log to the 4th x dx. Let's do this one fast. So we have u equal to log to the 4th x, therefore du is equal to 4 log cubed x times 1 over x dx. dv is equal to dx, and v is equal to x. We have uv, which is x log to the 4th x minus the integral of v du, which is 4 times the integral of log cubed of x dx, which we just solved above. Plugging in the result from above, we have x times log to the 4th x minus 4 times x log cubed x minus 3x log squared x plus 6x log x minus 3 times 2 times 1 times x. And let's distribute the negative 4 out, and we get x times log to the 4th x minus 4x log cubed x plus 12x log squared x minus 24x log x plus 4 times 3 times 2 times 1 times x. I think you're starting to see the pattern at this point. We are essentially generating a factorial right here. And what we want to do is figure out a way to isolate that factorial. Well, what can we do to do that? Well, let's take a look at our first integral, which was the integral of log x dx. What would happen if we evaluated this integral from 0 to 1? Well, let's see. If we evaluated this result from 0 to 1, we would get 1 times log of 1 minus 1 times 1. Log of 1 is just 0, so we have 0 minus 1, which is a negative 1, minus, now we got to evaluate this at 0. We get 0 times log of 0, and log of 0 is negative infinity. But that results in an indeterminate of 0 times negative infinity. We need to evaluate the limit as x approaches 0 of x log x. And rewriting this, we have the limit as x approaches 0 of log x over 1 over x. And using L'Hopital's rule, we can take the derivative of the top and the bottom, and the limit should be the same. So the limit as x approaches 0 of the derivative of log x, which is 1 over x, over the derivative of 1 over x, which is negative 1 over x squared. Simplifying this, we get the limit as x approaches 0 of negative x. And as x approaches 0, negative x is just 0. So now we know that at 0, x log x is effectively 0. And so we have 0 minus 1 times 0, which is just 0. And so this integral of log x from 0 to 1 is just equal to negative 1. Now let's take a look at our next integral. When this one is evaluated from 0 to 1, let's see what we get. Well, we know that every term that has a log x, when x is equal to 1, that log x would just be equal to 0. So every term here that has a log x would just be 0. And so we are left with the 2 times 1 times x, and that just gives us 2. And minus this evaluated at 0. Well, using our same exact technique that we used above, taking the limit and using L'Hopital's rule, we would find that this equals 0. We would see that this also approaches 0. And so we're left with the 2 times 1 times x, and when x is 0, that is also 0. So our final result here is 2 for this integral evaluated from 0 to 1. Now let's evaluate our log cubed of x from 0 to 1. Again, we have at 1, every term that has a log of x would be canceled out to 0. And so all we have left is the negative 3 times 2 times 1 times x, and at x equals 1, this just evaluates to negative 6. And then minus this whole thing evaluated at 0, and again using our technique with L'Hopital's rule, we would see that this approaches 0, this approaches 0, this approaches 0, and therefore we're left with negative 3 times 2 times 1 times x. And when x is 0, this is just 0. So our answer here is negative 6. And finally, our next integral of log fourth x from 0 to 1 is as follows. Evaluating this at 1, again, every term with log x goes to 0, and so we're left with 4 times 3 times 2 times 1, and at x equals 1, that is just 24. And then minus, evaluating this at 0, this approaches 0, this approaches 0, this approaches 0, and this approaches 0, leaving us the last term, when x is 0, is also 0. And so our result here is 24. So, taking a look at our results thus far, we see that the integral of log x from 0 to 1 is negative 1, or, in other words, negative 1 factorial. We see that our integral from 0 to 1 of log squared of x is 2, or 2 factorial. We see that the integral from 0 to 1 of log cubed of x is negative 6. In other words, negative 3 factorial. And we can see that the integral from 0 to 1 of log to the fourth of x is just 4 factorial. So the interesting thing here is we've effectively created a factorial generating function. However, we notice that the signs are alternating. It's going from negative to positive to negative to positive. And you might be wondering, what about log to the 0x? Well, we can also prove that quickly here. The integral of log to the 0th power of x dx, well, just equals the integral of 1 times dx, which is just x with a coefficient of 1. And so factorial of 0 is 1. And so we're going positive to negative, positive to negative. So we have figured out that the integral of log to the n of x dx is just equal to n factorial. However, it has a negative 1 to the n term because the sign is alternating. And so when n is 0, our sign is positive. When n is 1, our sign is negative. When n is 2, the sign is positive, and so on and so forth for each factorial value. Now, we don't want this alternating of the factorials. We want to solve for n factorial. So let's do that. N factorial would be equal to this whole integral divided by that negative 1 to the n term. So we can have 1 over negative 1 to the n times the integral of log to the n x dx. Now we can bring that coefficient inside the integral to get log to the n x over negative 1 to the n dx. And since the numerator and denominator both share the same exponent, we can write this as follows: log of x over negative 1 to the n dx, which is just the integral of negative log x to the n dx. Well, what is negative log x? We know based on our logarithm rules that a coefficient in front of the log is the same as log of x to that coefficient. And so x to the negative 1 is just 1 over x. And so we can rewrite this as follows: the integral of log to the nth power of 1 over x dx. And so we have figured out that n factorial is just equal to the integral of log to the nth power of 1 over x dx. Now, you might be wondering, well, this doesn't look like the gamma function. It seems to do the same thing, but it doesn't have that same structure that is notoriously known. Well, all we have to do here is a change a variable. And pardon me, this should be evaluated from 0 to 1, of course. And let's define u as log of 1 over x. This would mean that negative u is equal to log of x, which would mean that x is equal to e to the negative u, which also means that dx is equal to negative e to the negative u du. Using all of these, we can rewrite our integral with this change of variable, and we get the integral with different bounds. We have to evaluate the new bounds. When x is 0, we have log of x equal to negative infinity, and so negative u is equal to negative infinity. Therefore, u is just equal to infinity, so this bound would be infinity. And at 1, when x is equal to 1, log of 1 is just 0, and therefore negative u equals 0 and u equals 0. So our upper bound would be 0. And substituting log of 1 over x with u, we have u to the nth power times dx. And dx is equal to negative e to the negative u du. We can bring the negative outside the integral, and we have e to the negative u du. And what we want to do here is swap the bounds of the integral. Doing so would negate the integral, removing the existing negative sign. So we get the integral from 0 to infinity of u to the n times e to the negative u du. Fantastic. So this is equal to n factorial. Now this looks a little bit more like the gamma function. However, you might realize that the n term is not shifted. Well, that's because the gamma function is actually defined as such. Gamma of n plus 1 is equal to n factorial. Now, why is this the case? Why do we have a shift here? Well, the real answer is nobody really knows. It just became a convention for whatever reason, and there's lots of debate between whether the gamma function is better off shifted or unshifted. In fact, there's an interesting math exchange thread online with lots of people going back and forth about whether or not this shift in the gamma function makes sense or not. Proponents of it say that certain formulas look better with the shift, and detractors say that certain other formulas look better without the shift. And at the end of the day, all we can do is just accept convention. It's similarly to the debate between pi and tau, whether the circle constant should be defined by its diameter or its radius. But in any case, as I said, convention is convention. So on that note, we can replace our n factorial with gamma of n plus 1. So we have gamma of n plus 1 equal to the integral above, which is the integral from 0 to infinity of u to the n e to the negative u du. And if we want to find just gamma of n, we could plug in n minus 1 for n, and we would get the integral from 0 to infinity of u to the n minus 1 e to the negative u du. And that's our answer. Now, some of you guys are more used to seeing this in terms of x, so let me just go ahead and write that. So we have the gamma function at n equal to the integral from 0 to infinity of x to the n minus 1 times e to the negative x dx. We have arrived at our notorious gamma function. I really hope you all benefited from this video and hope that you all came out of this truly understanding where the gamma function comes from. If you enjoyed the video, please drop a like, subscribe, leave a comment, and share with all your fellow math enthusiasts. Thanks for watching, and I'll see you next time. Bye-bye.